Hi everyone, I'm Peter Chang from SkyMiser. I am going to introduce Tiny ONNC MLIR-based AI compiler for IoT devices. I will introduce Tiny ONNC and MLIR first, and then I will introduce how to use MLIR to support various AI frameworks. Then I will introduce Tiny ONNC's optimizations. Finally, I will show experiment results to you. Okay, first introduce Tiny ONNC and MLIR. ONNC is Open Neural Network Collection. It's a versatile toolkit for AI on-chip system, which includes complete toolchain, including compiler, calibrator, and semi-hosting runtime. It also includes execution platforms, include precision simulator, behavior simulator, and SoC virtual platform. ONNC support popular neural network frameworks, including PyTorch, Tensorflow, Keras, and TVM. So you may have basic concept about ONNC. How about Tiny ONNC? Actually, Tiny ONNC is ONNC for IoT devices, especially for ARM Cortex-M. For users, they can use PyTorch and TensorFlow Lite for training, and they could use model training by PyTorch and TensorFlow Lite to ONNC. ONNC will compile this model for ARM Cortex and devices. In your development board, you can use ARM Cortex CMSIS neural network library to run these models. And that is Tiny ONNC. Okay, you can have a basic idea about Tiny ONNC and ONNC. So how about MLIR? MLIR is multiple level intermediate representation. It's a flexible infrastructure for modern compilers. MLIR intended to be a hybrid IR which can support multiple different requirements in a unified infrastructure. By using MLIR, ONNC could support various machine learning frameworks as input, including PyTorch, TensorFlow, Keras, and TVM. So I think you have basic idea about ONNC, Tiny ONNC, and MLIR. So let's take a look how to use MLIR to support various AI frameworks for ONNC. How to apply MLIR framework to ONNC? We think the key is create a new dialect and then implement the lowering between dialects. Dialect is MLIR's terminology, which means consists of a set of defined operations. So you can use dialect to describe a kind of IR like ONNX, like ONNC, or like TensorFlow. And when you want to convert one IR to another IR, you need to implement a lowering, which means a conversion between different dialects. So we use this approach to support TensorFlow. Let's take a look. In the very first version of ONNC, we implement the backend of ONNC to generate code, and we implement ONNC dialect as our front end. Also, we implement ONNX dialect as our front end. By doing so, we could support ONNX model as our input in the very first version. But in the next version, we want to support a TensorFlow model. What we have done is implement the TensorFlow dialect. And also we implement the lowering between TensorFlow dialect, and ONNC dialect. By doing so, we'll not only support ONNC model, but also support TensorFlow models. For more detail, you can check this. In the first step, we create a new dialect for ONNC by MLIR's domain-specific language. Like the code shows, we implement convolution, which is a ONNC operator. We use MLIR's domain-specific language to describe the convolution's behavior. And when we implement a new dialect, we implement many operators defined by ONNC. And then we will implement the lowering between other framework to ONNC like this. We implement the lowering between TensorFlow and ONNC. We convert TensorFlow light operator called fully connected to ONNC. And because ONNC don't have one specific operator, we need to convert fully connected to two operators, GMM and ReLU. So we use MLIR's domain-specific language to describe a lowering like this. We describe TensorFlow light fully connected operation. We define this and convert it to GNN and the ReLU operation, as you can see in the code we present here. So we wrote many operators to define ONNC and the TensorFlow light dialect. And then we also implement lowering between TensorFlow dialect and ONNC dialect. So we use the same approach to support other frameworks like TVM. TVM is an open source machine learning compiler framework, and which means it's not only a machine learning compiler, but also machine learning framework. Users can train their model in TVM and use a model generated by TVM to compile it and get a machine code by TVM. So for us, we want to use TVM's front end, but we want to use our ONNC as a backend. So we use relay high-level IR of TVM as ONNC's input. As you can see in the right-hand side figure, that's TVM's compilation flow. They have their front end, and they use relay as their IR, and then they have their backend. And we use IR and their front end as our input. And we use ONNC to replace their backend. And how we do that? We use the same approach as you have saw in the TensorFlow. We have ONNC's backend, ONNC dialect, ONNC dialect, and we implement relay dialect, and also we implement lowering between relay dialect and ONNC dialect. So we could use TVM's front end and TVM's relay as our input. So we could use a model from TVM and use our ONNC compilers optimization technology to optimize these models and generate a binary through ONNC compiler. So we don't stop at that. We use the same approach to support Keras. Okay, we use the same approach to support Keras. We use Keras to TVM. We import Keras to TVM and use TVM's relay as our ONC's input. You put Keras into TVM and use the output from TVM to ONC and use this sequence. We could compile Keras model through TVM and the MLIR framework, then ONC. And that's what we have done to use MLIR to support various machine learning framework as our input. So I think as above mentioned slides, you could have a basic concept about how we have done to use machine MLIR to support Tensorflow, TVM, and Keras. And in following slides, I will introduce Tiny ONNC more detailedly. I will introduce Tiny ONNC optimizations. Let's take a look. ONNC is not only a compiler, not only a software, it's a hardware aware, especially architecture aware compiler, which means we can deeply understand the communication between SoC. And as you can see, the 95% of execution time actually spent on the communication between different components in SoC, like the communication between SRAM and the memory, the communication between memory and DLA. So to observe the potential optimizable parts in the SoC, we could gain 4.8 times speed up in one of our cases through ONNC's optimization, thanks to deeply understanding about SoC behavior. Also, you may wonder, how about precision? Okay, about precision, we use ONNC Calibrator to ensure precision by architecture-aware algorithms. As you may know, many DLA, they use integer in their DLA instead of floating point, but lots of data use floating point, especially in trained models. So how to convert, how to quantize this data is very important to ensure accuracy and use the DLA. So ONNC, because ONNC Calibrator is an architecture-aware algorithm, we could use many hardware support in DLA when quantizing. So ONNC knows tremendous suitable quantization points in DLA, and for some DLA, they have many hardware support to convert terminology called requantization. They convert like INT32 to INT8. These hardware support, we could use the ONNC Calibrator to fully utilize them. So by doing so, we could design a good calibration algorithm to use utilize this point and keep a high precision when you use integer-based deep learning accelerators. So we talk about performance, we talk about precision. How about memory? ONNC also saves SoC's SRAM, which is a very important part, especially for IoT devices, because most of IoT devices only have like 500 or even 128 kilobyte SRAM. So we use, because we're a compiler, especially we are architecture-aware compiler, we could fully utilize the communication between components, and we can use like a layer splitting approach algorithm to optimize the memory usage. We could also understand the spatial locality of different activations. We will provide more details, more performance, more SRAM numbers and performance number in following slides. And finally, about SRAM, we are not only reduce memory usage in SRAM, we could also recycle SRAM. What does it mean? In SRAM mass production, there's high quality SRAM, of course, but there are also some low quality SRAM, which means these SRAM, they have some fault, some failure die in their SRAM chips. But by our SRAM fault mitigating technology, we can effectively recycle this low quality SRAM and also provide, you can use this low quality chip, but again, high quality model performance and model precision by our SRAM fault mitigating technology. You could check more detail in our VLSI DAT papers. Okay, you have seen many like while we support AI frameworks and ONNC's optimization technology. So how about our experiment results? Let's take a look. We use New Mountain NUMake IoT M487 as our development board, and we use MLPerf Tiny as our benchmark, and we compare ONNC with Tensorflow Lite for micro. In memory usage, in our best case, ONNC is only 3/5 of TFLM. In code size, ONNC is only 1/10 of TFLM in our best cases. And you may wonder, does we sacrifice performance or accuracy to gain this memory or code size usage? No. ONNC reduce memory and code size usage without large performance drop and accuracy drop, as you can see in these two performance numbers and accuracy numbers. Furthermore, we gain better performance in image clarification case. So that's what I want to share to you today. And thank you for listening. And feel free to contact us through sales@skymeister.com. And you can ask any question in the chat box. Thank you.